So for our next speaker, we have Nigel Hitchin connecting remotely, who will speak about deformations, a personal perspective.
Okay, so thank you for the invitation to talk at this meeting, and also thank you for suggesting that some of the talks might be historical. So a large part of my talk, in fact, will be historical, about somehow my encounters with deformations and Kuranishi method over the years. So let me share my screen and let me see whether this is going to work. How's that? Is that okay? Okay, well, I guess so. Okay, so this is my first encounter with deformations. The theorem that Yao mentioned in his introduction. So this was a announcement in the Proceedings of the National Academy back in 1977, and right at the end, as you see, we appeal to the general theorem of Kuranishi, which guarantees that the infinitesimal variations, which is what the main point of the paper is about, really integrate to give genuine local variations. So in fact, as we were working on this problem of instantons and infinitesimal deformations, it was Singer who pointed out that actually Kuranishi's approach ought to be possible to use in this context to produce a local moduli space. So that was in a way, my first engagement with deformation theory and Kuranishi in particular. So in this talk, I want to give a personal perspective on the various pieces of mathematics which have involved variations over the years, but I also want to include some other personal perspectives, which are those of Kodaira, in fact. So this book was published in 1985, so that's about 25 years after Kodaira and Spencer first started working on deformations of complex structures. And most of it is a comprehensive introduction to the theory, but the interesting aspect of it is that he inserts various recollections and various comments about what they thought at the time. And so somehow I'll mix my own personal perspectives with those of Kodaira. So by 1985, of course, Kuranishi's theorem was well known, and so this is the way it appears in the book. There is the theorem. It was any compact complex manifold, there exists a complete complex analytic family. But Kodaira follows this up with another comment. As you see, the theorem is ineffective in explaining that M coincides with the dimension of the H1 of the tangent sheaf for various M. Nevertheless, it is obvious that it's of fundamental importance in the theory of deformations of complex structures. So how do we interpret this? Well, Kodaira's obsession is the relationship between M, the number of moduli of a complex manifold, and the dimension of this infinitesimal space, this tangent, H1 of the tangent sheaf. And I think all the time he was looking for strict criteria that tell you when M is equal to this dimension. Somehow the fact that we have a complex analytic family, which of course might be singular, somehow for him it seems it doesn't solve his problem. But of course, as he says, it's fundamentally important. Actually, what he goes on to say is the following. You see that? This reflects a fundamental difference between mathematics and physics. In physics, if a theory is developed for the purpose of explaining a certain phenomenon and it fails to do so, then that theory must be useless. Well, I think the context that I've had with deformation theory, I'm not sure how useful they are in the physics, but certainly the physics has motivated a lot of them. So let me start with this this issue of instantons. So this is going back to 1977 when Singer came to visit Michael Atiyah in Oxford, and he brought with him this problem from the physicists of finding self-dual solutions to the Yang-Mills equations over R4. So the situation, as it was then, is that we're looking for connections on structure group SU2 on a bundle over R4, that the curvature should be square integrable, and that the self-duality equations, namely that if the curvature, which is a two-form with values in the Lie algebra, if this is self-dual with respect to the Hodge star operator, then this gives a minimum of the integral of the square of the curvature. And then the issue was trying to understand all solutions modulo gauge equivalence, and more generally, is there a moduli space, and if so, what dimension is it? So the approach, the variational approach, the infinitesimal variation, went like this, that if you want to consider an infinitesimal variation of the connection by a gauge transformation, then, well, an infinitesimal gauge transformation is a section of the Lie algebra bundle, and then the deformation of the connection is given by a one form with values in the Lie algebra, which is the covariant derivative of psi, or I've written it here as the covariant exterior derivative. And then the deformation of the curvature, given any A dot, is given by A dot being alpha here, is the exterior covariant exterior derivative of alpha. If you want that to be a self-dual connection, if you're starting with a self-dual connection and the variation is still self-dual, then that means that the anti-self-dual part must be equal to 0. So that lies in the anti-self-dual two forms with values in the Lie algebra. So you put these together and you see that there's a short elliptic complex. The image of dA here consists of infinitesimal gauge transformations acting on the connection. The kernel of this is where you want your variation to be. And so the quotient of the kernel of this by the image, H1 of the complex, should, under good circumstances, give you the number of degrees of freedom in this infinitesimal level. So the equations are conformally invariant. And so at that time, we didn't have the theorem of Uhlenbeck, which guarantees that when you have L2, finite L2 norm of the curvature, then the metric or the connection extends to the sphere, but it was a useful assumption because it was clearly satisfied by the examples that we had at the time. And so when you extend this to a principal SU2 bundle over the four sphere, you get a topologically invariant, the Chern class. And then the Atiyah-Singer index theorem gives you the alternating sum, which turned out to be 8k minus 3. And then positive curvature, together with the self-duality of the connection, tells you that the harmonic forms in the H2, in the two-dimensional degree 2 forms in this complex are equal to 0. And if k is not equal to 0, then looking at SU2, we know there are no harmonic 2 forms on the four sphere, so H0 is equal to 0. And so that gives you the H1 as dimensioning with dimension 8k minus 3. And then Kuranishi, you adapt Kuranishi's method to get a local moduli space. So that is the, okay, that it seems obvious now, but perhaps at the time, the whole concept of looking at connections, a huge space of connections and the equivalence under gauge transformations was quite novel, at least to not so much perhaps to physicists, but certainly to differential geometers. So maybe I could just point out like a background to this as far as I was concerned, because that complex, at least without the connection, was kind of familiar to me, because I wrote my thesis a few years before that, which was about the Dirac operator, and it involved index theory, Weizenbach vanishing theorems, and conformal invariance. And in the years that followed, I was particularly interested in conformal invariance. So in particular for the Dirac operator. So if you take a metric and you make a conformal change, if you multiply by f squared, where f is a non-zero function, then if you want to see how the solutions to the Dirac equation transform, then you have to scale it by a certain power of f, which turns out to be n-1/2 in this case. And of course, when you apply the Dirac operator, then you're going to another copy of the spin bundle with a different scale. So it always increases with the first order operator. It increases by 1. And so, but the point here was that if you have a spinor solution to the Dirac equation and you consider it as a conformal invariant object, then the inner product is not a function at each point, but it's something which transforms as f to the n-1, which means you can actually integrate it over a hypersurface. So what I was looking at were, for example, this type of problem where you have a smooth domain in Rn, and you look for solutions to the Dirac equation on the inside, and you look at boundary values which are L2. So you set up a kind of Hardy space, and then evaluation at a point on the interior gives you a conformally invariant kernel, Sago kernel, which gives you a conformally invariant metric of complete negative scalar curvature on this domain. Well, I was using that for the Dirac operator, but there were many other conformally invariant operators, and in particular this one. So there was this complex. You start with the anti-self dual middle dimensional forms on in even dimensions. And again, you could now look at the conformal weight here is m instead of the n-1/2. That means you can integrate the norm squared of this over the interior. And so you could consider, for example, a Bergman kernel instead of a Sago kernel. But anyway, there was this complex. In 4 dimensions, it's going from omega-2 minus to omega-3 to omega-1. And of course, there's a dual complex, which is this. So these complexes actually were kind of familiar to me, but certainly not in the context of self-dual connections. So it was relatively straightforward to, once the problem arose, to kind of put in the connection and see that the vanishing theorems and the index theorem would give you something. But what did it give? Well, so the situation was at the time was this, that the physicists had provided us with some examples of self-dual connections, and but this was a 5K plus 4-dimensional space of such things, and for quite a long time there was no way of getting more than this. But once we had the index theorem and the complex, told us that there were 8K minus 3 parameters, and so we were missing some. And so then the challenge was to find how to construct the extra ones. And ultimately, it was in this paper where we gave a construction of all solutions, filling in those 8K minus 3 parameters. So in a way, Kodaira's version of this, if you like, a similar problem that he had was this. This is what he refers to in the book. He was looking at calculating moduli for various families, and in particular for hypersurfaces in projective space. And he came up with a problematic example, quartic surfaces in P3. So as you see, he gets well, it counts parameters and it gets 19, but the dimension of H1 is 20. And so, as he says, this seems very strange at the time. Nothing was known concerning the existence of deformations of quartic surfaces. It may be said that the theory of deformation was at first an experimental science. And indeed, in terms of the instanton problem, it was certainly an experimental science. And for him too, it was a way of trying to find out things about deforming complex manifolds. And so here is how his problem was resolved. That Nakano pointed out that actually if you take one particular quartic surface, then you can also see it as an elliptic surface. And so using Kodaira's earlier work on elliptic surfaces proved that actually you could deform away from quartics into giving another dimension of looking at elliptic surfaces, what we now call K3 surfaces. So in some sense, that sort of aspect of Kodaira's experience was kind of reflected in this instanton problem. That the problem was to find missing solutions to the Yang-Mills equations that were not known at that point, but were predicted by a calculation of the infinitesimal deformations. So having encountered this interesting problem in gauge theory, there was another one which came from a physicist. This was a problem of Yang-Mills Higgs equations and magnetic monopoles. So here we're on R3, and we have an SU2 connection on a bundle over R3, and an extra Higgs field that's in a section of the Lie algebra bundle. This satisfies certain conditions at infinity. The length goes to 1 as x goes to infinity. And so in particular, this gives a map from a large two-sphere to a two-sphere inside the Lie algebra. This has a degree, which is called the charge of the monopole. And there's a Yang-Mills Higgs functional whose critical values are given by, well, whose absolute minima are given by these Pogomolny equations here. So the curvature is here a two form with values in the Lie algebra, and we take the Hodge star of the covariant derivative of the Higgs field, and those are supposed to be the same. So the difference here with the instanton problem is that it's not conformally invariant. We can't compactify this. However, the equations themselves were recognized to be related to self-dual Yang-Mills equations as solutions which are invariant under translation in the fourth direction. So locally, you could write the connection as a connection in 3 dimensions plus the Higgs field times the fourth coordinate. More invariantly, you would say that if it's invariant by translation, then there's the action of a Lie derivative on the bundle, but there's also the covariant derivative in the direction of x. And so the difference of those is, invariantly speaking, what the Higgs field is. And so one wants to understand the deformation complex for this problem. Well, given that it's the self-dual Yang-Mills problem invariant under translation, then of course you can just split up the complex that I've just talked about into pieces. And the first part, of course, involves here the derivative of the infinitesimal gauge transformation. Here is its action on the Higgs field, and here's the rest of it. So we have this deformation complex now, but we can't compactify. And so the question of actually looking at trying to look at an index theoretic calculation is a much more complicated one. And it was so Cliff Taubes who actually found the right function spaces to actually find this dimension. On the other hand, it wasn't such a crucial issue at the time. And this is so this is reflected in a way going back to Kodaira. So as he says, to his surprise, sometimes it was far more difficult to calculate the infinitesimal deformations than actually to calculate the moduli. And I think perhaps this is a situation. So because now why is this? Well, because actually from various points of view, one knew what the dimension of this monopole moduli space was. So, and there were physical calculations. There was also a rough calculation by Eric Weinberg, but there were some more constructive ones by Corrigan and Goddard. And I wrote this paper relating the problem to spectral curves. So here is how the dimension count appears in as far as spectral curves are concerned. So I showed that a monopole actually is defined by a spectral curve, by an algebraic curve in the total space of the tangent bundle of the projective line. So this is given by an equation like this, where the coefficients A1 up to AK are even degree polynomials in Z. So the number of parameters for the spectral curve is equal to this. On the other hand, the curve is constrained by the fact that there's a certain invariant degree 0 line bundle, a transcendental line bundle over TP1. And the constraint is that that should be trivial on the spectral curve. So the spectral curve has genus k-1 squared. So this gives you the difference, which is 4k-1. So this is 4k-1 real dimensions. So real dimensions is a reality condition you put into this. Of course, I mean, you might say this is not, I mean, this is kind of implicitly assuming that the spectral curve is smooth and so on and so forth. But still, somehow this number there were constructions of realizing this number of parameters, and there were clearly no more. On the other hand, there was an even stronger result coming from Simon Donaldson, who showed that you could actually describe very explicitly what the moduli space of monopoles was. That there was a circle bundle over this 4k-1 dimensional space, which was isomorphic to the space of base degree k rational maps from P1 to P1. So you just write down a rational function like this. So this is taking infinity to 0, taking one base point to another. And what is it then? It's just the pairs of polynomials P and Q, such that the resultant is non-zero. So this was an even stronger realization of the moduli space. And it came about through, so there was less dependence here on the infinitesimal deformations and the use of Kuranishi, and alternative methods giving a way of understanding what this moduli space was. And it involved this Nahm's equation, so the Nahm transform, which was going from these equations in 3 dimensions to some formally similar equations in 1 dimension, these nonlinear ODEs with boundary conditions. And in fact, Nahm produced this method of solving the monopole equations by analogy with what we'd done with instantons, which was giving an equivalence between this 4-dimensional PDE problem and an algebraic equation for quaternionic matrices. So by this time, there was a sort of framework of hypercalar geometry or quaternionic geometry, which is coming into play, and gave different viewpoints on this. So on the other hand, if you want to see this quaternionic structure at the infinitesimal level, then you can use, in fact, it was pointed out in Taub's paper, probably before Donaldson's theorem was proved, that there was this quaternionic structure. That if you look at the deformation equations first order deformation equations and we impose the harmonic condition as well, then we're looking at harmonic forms under this harmonic with respect to these Ds. And you can rewrite the deformation as, if you like, a quaternion. And you see there that there's, if you like, I, J, and K, there's a complex structure for each direction in R3. And so for each direction in R3, you get a complex structure, which is, thanks to Donaldson, isomorphic to the space of rational maps. So, so this is more a question, not so much of finding the dimension of a moduli space, but noticing some geometric property of it. In this case, that there was a hyperchalis structure. In fact, okay, the infinitesimal part here tells you that there's some sort of quaternionic structure on the tangent space, but it doesn't tell you actually that this is integrable, and if you like, that the complex structures given by all I and J and K are integrable. That depends on other input. So this is a little bit like something that Kodaira mentions. It's a little bit surprising nowadays to see this, but he says that at first we didn't notice the fact that the deformation parameter is actually in general a complex one. So I think if you think about it, it's a fair enough comment that if you think of a complex structure as being given by a tensor, I squared equals -1, then you look at the infinitesimal deformations of that, and of course you have what I dot plus I dot I equals 0. And you could notice that conjugating by I dot gives you by complex structure, gives you another one. But even so, that's saying that the tangent space might be complex, but you need to know a bit more that the actual moduli space is complex. So even in some sort of primitive sense, recognizing that the moduli space for deformations of complex structures is actually complex was not a trivial one in those early days. And equally, observing the hyperchalis structure on these moduli spaces of instantons and monopoles was something which was not immediately obvious and required some other input. Okay, so then having looked at gauge theories in 3 dimensions and 4 dimensions, it seemed to me that there was something going on in 2 dimensions. And so you could look at, say, solutions to self-Julian-Mills on R4, which are invariant under translation in the last 2 directions. So then, as before, you get 2 Higgs fields, phi1, phi2, and a connection in R2. And so you can organize the infinitesimal variations as in terms of quaternion. That was something which was by that time clear that one ought to do. And then you see that, that there's a sort of essential difference now, that if you take complex structure I, if you like, if you're matching phi1 and phi2, A1 and A2, then the obvious thing to do is to put together the 2 Higgs fields into a complex one, and the 2 components of the connection into a D-bar operator. But if you look at the complex structure J, then you match phi1 with A1 and phi2 with A2, and then you can put those together to be a complex connection. So rather than the situation with magnetic monopoles, where all the complex structures were all equivalent, different but equivalent, in this case, there's a rather different picture. And the equations here are the equations which are just the dimensionally reduced self-dual Yang-Mills equations. So this was something I was looking at somewhat later than the instantons and monopoles. And in fact, it wasn't a problem that came from physics. So the equations had appeared in the physics literature, So here they are, for example, in the paper in 1977. And as the author says, unfortunately, in this case, the model is not interesting because the action is always zero. So what that means is that actually there are no solutions on R2 where the curvature is in L2. So there are no finite action solutions in R2. And so these equations were dispensed with by the physicists. On the other hand, I'm not a physicist, I'm a geometer, and I could see that actually they were conformally invariant in a rather different sense than the original instanton equations were conformally invariant. And that meant that you could actually put them on a Riemann surface, and in particular on a compact Riemann surface. So if you're on a compact space, then Kuranishi's method is going to work much, much better than trying to make it work as the monopole problem in R3. So, so the interpretation then, the invariant interpretation of these equations was that if you take complex structure I, then you have this complex object here, phi, and the d-bar operator. So phi now becomes a holomorphic section. So V, so this d-bar operator defines a holomorphic structure on the underlying C infinity bundle V. And phi, big phi, the Higgs field, is then a holomorphic section, not of the endomorphisms, but to get conformal invariance, you have to twist with the canonical bundle. And then the connection itself, the unitary connection, in these terms, means that the curvature of the connection, which is given by the inner product and this d-bar operator, this is related to the Higgs field by this equation. On the other hand, the complex structure J is where these two objects are the covariant derivatives of a connection, a GLNC connection, and the equations say that this is flat, or that this dA plus phi star, which is essentially this thing, is actually going to be a flat connection. So we have this relationship, which turned out to be very productive, between some holomorphic objects here and some gauge theoretic objects here, where the connection is perfectly flat. So you can look at the deformation equation then, the deformation complex for this in two different ways, well, in many different ways, but in particular with the complex structure I and complex structure J. So complex structure I looks like this. Okay, so we have sections of the endomorphism, the d-bar operator takes you to the variation in the complex structure, and then this, the conjugating by phi, gives you this variation of the Higgs field, and so forth. Or you could look at it from the point of view of complex structure J, and then it turned out to be just basically the de Rham complex for a flat complex connection. Anyway, this is all over a compact manifold surface, and the index theory is very simple. So we get an index which gives you a dimension for a moduli space, and one now can do we can work with the Kuranishi type of approach and produce a moduli space which is a hyperkähler manifold. Now I'm essentially a differential geometer, so I was these deformations were all, for me, done in terms of Dolbeau theory or harmonic forms. But it was pointed out somewhat later that that you can see this as a double complex. So it's really the hyperchomology of a double complex. So we've got the d-bar operator going this way, and the bracket with phi going this way. So, well, this paper of Biswas and Ramadan set it into a rather bigger framework. But that actually, in hindsight, pointed out that looking at deformations, infinitesimal deformations, can actually identify certain important features of the moduli space. So in this particular case, then you have this double complex. So there are two spectral sequences associated with this, which are related to the sheaves which are given by the kernel sheaves of this one. So this is looking at things which the sheaf of local sections of this which commute with phi, and the kernel of this. So there are two ways that these two spectral sequences give you two ways of looking at this hyperchomology. The first one is the one which is kind of obvious, I suppose, that you're looking at a variation of a pair of objects, the vector bundle, holomorphic vector bundle, and the Higgs field. So this is the variation in the holomorphic structure of the vector bundle. And if you fix that, then you're varying the Higgs field. It's a holomorphic section of this. And more globally, you could say that if you're looking at the pairs of Higgs fields and vector bundles where the vector bundle is stable, then this is giving you a map from an open set in the moduli space to the moduli space of stable bundles. And the fiber is this, which is the cotangent space. So this is a realization of an open set in the moduli space as basically the total space of the cotangent bundle of the moduli space of stable bundles. But the other one, if we look in the other sequence, gives you this. And now what is phi? So phi is regular at each point. So in the sense of an element of the Lie algebra, then its centralizer is spanned by 1, phi squared, etc. And phi is not a section of the Lie algebra bundle, it's a section of that twisted with k. So actually the kernel is isomorphic to, so this is the image of k inverse, this is the image of k to the -2, and so forth. So actually, when you look at the map here to sections of the co-kernel, you're looking at a map to direct sum of holomorphic sections of the powers of the canonical bundle. And this is realized by a map, this map looking at trace of phi to the I, where you take the Higgs field and take trace of the power. So in a way, although this is the integrable system on the moduli space of, what we're getting here are two Lagrangian fibrations on on open sets of the moduli space of Higgs bundles. And of course, both of them have been put to great effect since. But what I'm pointing out here is that actually they are visible in terms of the deformation complex. Okay, so those are examples, if you like, of deformations being used to solve problems, constructing spaces of solutions to gauge theoretic equations. So for the second part of this talk, I'm going to look at two different issues where the question is more, what does the deformation theory suggest? That somehow there's a reason for looking at this deformation theory. And if you look at it and focus on certain aspects of it, it suggests some things which might be true, and the full implication of that has not yet been realized. So I want to know now, so we're going now back from gauge theory to diffeomorphisms. So some years ago, around the year 2000, I guess, for one reason or another, I introduced this notion of generalized geometry. So that so this was a way of extending the diffeomorphism group slightly in ways which related to a number of issues. But I mean, so the simple idea is this: that you talk about the generalized tangent bundle of a manifold as being the tangent bundle direct sum with the cotangent bundle. So sections of this are given by vector fields, and one forms. And if you have a two form B, then this acts on this space here. So it leaves the, sorry, this should be a capital X. It leaves the vector fields fixed, but it shifts the one form by the contraction of B with the vector field X. So this leads to a group, infinite dimensional group of what I call generalized diffeomorphisms, where you look at closed two forms and a semi-direct product of closed two forms and diffeomorphisms of the manifold M. So that acts on sections of T plus T star, and the action is, so it's like a Lie derivative, really. So it's this, that you, as far as, so y plus eta is a section of T plus T star, you act on it first of all with the vector field X by ordinary Lie derivative, and then you add on this, what's called B field action, are given by the exterior derivative, the two closed two form, which is d psi. And there's a sign there, which is a certain convention. So this is the substitute for the Lie bracket of two vector fields. It's not skew symmetric like the Lie bracket is, but it is an action. In fact, the failure to be skew symmetric is given by this. So there's an indefinite in the product on T plus T star, just given by pairing T and T star. So that's part of the geometry of this generalized picture. So then you have this idea of generalizing the notion of a complex manifold. So you think of a complex manifold in purely differential geometric terms as being an endomorphism of the tangent bundle whose square is -1. That defines a +1 plus I eigenspace inside the complexification. And the Newlander-Nirenberg theorem tells you that if you have two sections of this eigenspace, if the Lie bracket stays inside it, then that's equivalent to integrability in terms of local coordinates of the complex structure. So if you imitate this in this generalized setting, you say, let's take a complex structure on T plus T star, which is compatible with this pre-existing inner product. So that means it has to be skew symmetric with respect to the inner product. Then its plus I eigenspace gives you a subbundle of T plus T star complexified. And you say, well, we're going to call this integrable if two sections, if I take two sections, V, U, and V, then this generalized Lie derivative of V with respect to U should lie inside here. And in this case, actually, this condition tells you that, in fact, L is isotropic. So if you go back, if you see that if it's isotropic, then actually this bracket is skew symmetric. So okay, so this is like the Lie bracket of two vector fields. It's a skew symmetric bracket. And so so I gave this problem to my student Marco Gualtieri, and so it was something to be developed ab initio, and he made a lot of progress with it. Took him a long time to produce a paper, but it finally appeared in the Annals in 2011. So, so obviously the obvious question, part of his thesis, was what is the deformation theory of generalized complex manifolds? So in this case, so what we're looking at deforming a subbundle of T plus T star. So it's infinitesimally, it's a homomorphism from the subbundle to the quotient bundle. Now, because L is isotropic, then actually the quotient bundle is isomorphic to L dual, and in fact the deformations are skew symmetric. So this is because you have this orthogonal structure on it. So the complex turns out to be in this terminology, turns out to be fairly simple thing, that L is actually you can put it this way, that it's actually a Lie algebra. Okay, so L star is actually isomorphic to L bar. So L and L bar has a bracket on it. It has this, so it's a Lie algebroid, and this is basically, this is the Lie algebroid cohomology if you interpret L star as L bar. And the deformation class lies inside the degree 2 part of this complex here. And you can use Kuranishi's method to show that there's actually a local complex moduli space associated to this on a compact manifold. If the actual, so one of the reasons for looking at these generalized complex structures was that both symplectic manifolds and complex manifolds are both examples, two extreme examples. So if you start with a complex manifold, then this is what this subbundle of the complexified generalized tangent bundle is spanned by the d by dzi bars. These are the complex vector fields, and then these are the one form. So these together form the subbundle of the complexified generalized tangent bundle. And then this cohomology, okay, it involves, if your actual underlying manifold is now just an ordinary complex manifold, this cohomology is given by the cohomology of polyvector fields. And so in particular, the deformation space, the first order deformation, can be written in this way. So, so as you see, there are various pieces. This part here is just the deformation of the complex structure, at least in good situations. This is to do with the action of the two forms. But then we have this holomorphic sections of the second exterior pair of the tangent bundle. And so this is a question which arises then. What does this represent? What kind of deformations are there arising out of this? So we start with this general picture. We apply this general picture to a familiar object, and then we see that there are deformations, or in principle there are deformations, which seem to introduce something more interesting than just the complex manifold. So one of the tasks in Gualtieri's thesis was also to understand what it meant to have what was generalization of a Kähler manifold. So since a complex manifold and a symplectic manifold are both examples of generalized complex manifolds, then he said, what is the compatibility between the two generalized complex structures that a Kähler manifold has? And it turns out that there are two generalized structures which commute, and then there's a positive definiteness condition. And then it turns out that that out of this you get a holomorphic Poisson structure. I won't go into the details of it, but basically so what is a holomorphic Poisson structure? Well, it's in particular, it's a holomorphic section of this space, this bundle, which satisfies an integrability condition. This is the Nine-house bracket. So, but when you spell it out in terms of the underlying manifold, actually what you find is that it's what's called a bi-Hermitian metric. You get a metric G and two complex structures which are compatible with G, but they don't commute. So these generalized ones commute, but down here they don't. And the failure to commute is basically a real part of a holomorphic Poisson structure. Well, one for each complex structure, I plus and I minus. So if we're talking about these generalized Kähler manifolds, then we're in the realm of holomorphic Poisson geometry. And then there was an interesting deformation theorem of Ryushi Goto, that he looked at deformations of generalized Kähler structures. And so what he did was the following. He started with a family, a deformation of an ordinary complex structure via a Poisson, a holomorphic Poisson structure. So it turns out that for arbitrary t, this describes the subbundle L for a generalized complex structure. And then he starts with a symplectic structure defined by a Kähler form, and then tries to find by a power series expansion a generalized complex structure which commutes with the one given by this. And he succeeds in doing that, and using the Kuranishi method to show that the formal power series actually converges. So one of the interesting consequences of this, corollaries of this, was that if you have a complex Poisson manifold, then you have a Kähler form, omega. So this has a cohomology class in H1 of T star. You have the Poisson structure, which is the holomorphic section of this. If you contract one with the other, you get a class in here, which is the Kodaira-Spencer class of the deformation of this structure. And a consequence of this is that it's actually unobstructed. And I was quite impressed by this, but so then I gave a description, well, a slight generalization, but stripping away all the generalized geometry, all the things which started this whole picture, and giving a more conventional description of this deformation theory, and where you don't actually need to assume that omega is Kähler, and all you need is the DD bar lemma. So it's a little bit like Bogomolov's theorem for deformations of Hyperkähler. But anyway, so what comes out of this is that, for example, if you take projective space P2, then of course, okay, so then this class is zero. The actual deformation of the complex structure is trivial, but the deformation of the complex Poisson manifold is a genuine deformation, because the Poisson structure that you get out of this deformation is a holomorphic section of the anticanonical button. It vanishes on a cubic curve. So this is an elliptic curve, but as you vary in this deformation, then the normal bundle of this curve, this cubic curve in P2, changes. So it's an elliptic curve which is embedded in P2 in different ways. And now, if you go to you can do this with the Hilbert scheme of P2, and then you can understand, then you get a genuine two-dimensional space of deformations of the Hilbert scheme, which involve an elliptic curve and a translation. So these are the two parameters, the modulus of the elliptic curve and the translation on it. And okay, so anyway, the general impetus of this is that you're heading towards the basically non-commutative geometry. So at the moment, it's still unclear what the relationship is between generalized Kähler structures and non-commutative deformations. That Gualtieri and his colleagues, students and postdocs, have written a number of papers on this subject, and I think they're getting close to it. But there's no answer yet. But what is pretty clear is that this term, which appears in the deformation theory, is in some way related, in particular in a rather strong way, in the context of generalized Kähler manifolds, to non-commutative geometry. So these Sklianin algebras are non-commutative deformations of the homogeneous ring for the projective space. Okay, so that's an example of, if you like, examining a deformation complex, noticing something interesting about this term, then asking questions about what the actual finite deformations are really realizing in those directions. So to finish with, let me tell you about something which is now rather more speculative. And this is, if you like, a mixture of diffeomorphisms and gauge theory. It's treating diffeomorphisms as gauge transformations. So it's a very concrete picture in some respects. So if we have a hyperbolic surface, compact surface, And as we know, its universal covering is the upper half plane. And so we get an action of the fundamental group on the upper half plane. But it also acts on the space of oriented geodesics in the half plane. So we can think of the endpoints of those as being a pair of points in the projective line. And this is a symplectic surface. So this is the symplectic form if you parameterize it this way. And the fundamental group, of course, preserves this symplectic form. So we have an action of the fundamental group on this, this surface. Well, that, of course, is true for a general compact surface of negative curvature, not necessarily constant negative curvature. The geodesics in the universal covering are form a symplectic surface, in fact, a surface which is isomorphic to S1 cross R. So this is a convenient parameterization of it. So you fix a point in the universal covering, and you, given an oriented geodesic, you fix a point in a direction, if you like, then you look at the angle that the shortest distance, the geodesic of shortest distance makes with this geodesic. So if you like, so that gives you, okay, so at the moment it looks like T should be positive, but we're looking at oriented geodesics. So if you look at minus T and the angle phi plus pi, that's actually giving the geodesic in the opposite direction. So this is always a symplectic surface. It's always isomorphic to S1 cross R. In the hyperbolic case, if T is the hyperbolic distance, then this is the symplectic form. And so actually what we get here for any negatively curved compact surface is an action of the fundamental group on this symplectic manifold. In fact, it acts by Hamiltonian diffeomorphisms of S1 cross R. So if you like, from the differential geometric point of view, what we're looking at is a flat connection over sigma, where the structure group is the Hamiltonian diffeomorphisms of S1 cross R. So there are many questions you could ask about this. One is, well, is there a good infinite dimensional moduli space? Is it contractible? Are all points given by Riemannian metrics, the Riemannian geodesics? What you can say is that the holonomy by Crofton's formula defines the length of closed geodesics. And so we have Hotel's theorem, which is saying that the marked length spectrum gives the isometry class of the metric. So this is containing the holonomy of such a connection is containing a lot of information about the actual equivalence class of the Riemannian metric. So what is then a symplectic connection? So you're looking for a four manifold which fibers over the surface with fiber S1 cross R. And suppose we have on it a closed two form such that alpha wedge alpha equals 0. So that means it's locally decomposable. Then if alpha is non-zero on each S1 cross R fiber, then it has a degeneracy distribution, which defines a foliation if it's closed, transverse to the fibers, and that gives you a flat symplectic connection. And if alpha is exact, then it's the holonomy is contained in the Hamiltonian diffeomorphisms of S1 cross R. So well, you can do this. So if you look at the unit circle bundle of a surface, then there are these three canonical vector fields on it. You've got the circle action giving you a vector field Z. You've got the geodesic flow, which is horizontal, and you've got the complex structure or the conformal structure on the surface, which is horizontal. So which takes a horizontal vector field to another one, Y. So you've got these X, Y, and Z. These canonical vector fields, and they have their dual one forms. Eta is, for example, the connection form of the SO2 connection. And then, okay, so you can work this out. You can see that, in fact, you can define. So if you take a 4 manifold, which is this unit circle bundle times R, you can define on it an exact decomposable 2 form by this conform, naturally by this method here. So, for example, in the hyperbolic space, this is the in terms of these omega, theta, and eta, this is the 2 form. So it's exact and it's decomposable, very explicit. So that defines you a connection, and in which is a definition which transforms naturally under diffeomorphisms. So this is a way in which one can try and understand the action of the fundamental group in this geodesics of the universal covering. Now, of course, you can go from Hamiltonian vector fields to Hamiltonian functions. There's a little choice there, but then the deformation complex becomes quite simple. So H here, we're going to take the tangent bundle of M and decompose it as a sum of vertical and horizontal parts, and then H star, which is really just the pullback of the cotangent bundle of sigma. So we have this complex here. Okay, so if you like, the dA of a function f is the component of the derivative in the H star direction. So you have the deformation complex. And now, so finally, in this last couple of minutes, I just want to point out that if you start with the hyperbolic metric, then you can identify in a rather natural way certain elements in the H1 of the deformation complex, which arise from holomorphic sections of powers of the canonical bundle. So I've written this locally here. So we're using the upper half plane metric here. Then the real part of this expression here, so what is this? This is, if you like, a one form on sigma with values in functions on the fiber. You can think of it that way if you like. And this actually satisfies the dA of A equals 0. And so, well, when M equals 1, then all it is a holomorphic one form, of course, and then that doesn't give you any proper deformation of the actual symplectic connection, because it's just a choice of the Hamiltonian extension, going from the Hamiltonian vector fields to the functions. But you can show that actually when M is equal to 2, this is basically giving you this is an infinitesimal version of deformations through hyperbolic metrics. So quadratic differentials are parameterizing deformations through hyperbolic metrics. Deformations of the geodesics, the connection on the geodesics. What about M is greater than 2? Or more generally, suppose you have some infinite combination of these things, which you can understand as a CR function on the unit circle bundle. What happens? Well, I don't know what happens, but certainly there's a point of comparison which is suggestive. So we know that Teichmüller space is, we can think of this in various ways as the holomorphic sections of the square of the canonical bundle. We know also that actually there's a component of the moduli space of flat SLNR connections on a surface, which is isomorphic to powers up to n. And so what we're saying here is, well, is it possible that that if we think of Hamiltonian diffeomorphism of S1 cross R as somehow SL infinity R, that actually there is a good moduli space of symplectic connections, which is some vector space, some infinite dimensional vector space, which is some kind of limit of this as n tends to infinity. So this is of course an infinite dimensional question, and there are various features about it that I know nothing about, but there are some very suggestive issues. And so I want to, perhaps I should leave you with this. It's an example of, if you like, looking at a deformation complex and looking at the infinitesimal deformations and asking questions as to where they might lead. And that is, I think, one of the aspects of looking at the Kuranishi theory. Well, Kuranishi theory would not apply in this case, but looking at the structure of the deformation complex is something which can be very suggestive. So thank you very much.